Hello, everyone. I'm Eric Hyam, Technical Editor with Microwave Journal, and I'd like to welcome you to the next installment of our Technical Education webinar series. This webinar is entitled Achieving SWaP-C Goals with Qorvo's Highly Integrated Radar Solutions, and the webinar is sponsored by RFMW and Qorvo. Today's presentation will be given to us by Fouad Boueri and Paul Prudhomme, and both Fouad and Paul are senior product line managers at Qorvo. This webinar will provide an in-depth look at the critical aspects of size, weight, and power optimization in modern aerospace and defense systems, focusing on MMIC transmit-receive modules and Spatium solid-state power amplifiers. Qorvo speakers will explore the latest advancements in MMIC technology and TR modules, including the design, benefits, and integration into complex systems such as radar, communications, and electronic warfare. Attendees will gain valuable insights into the technical specifications, performance metrics, and integration techniques of these modules. The presentation will demonstrate real-world applications and performance achieved using Spatium technology in complex systems. But before we begin, let me cover a few logistics. If you'd like to download the presentation slides for reference, you'll find a copy in the handouts window. We'll have time for questions after the presentation, and to ask one, please type it into the Q&A window at any time. The presentation is being recorded, so it will be available to watch again and recommend to your colleagues. Now, let me introduce our speakers. With more than 22 years of diversified experience in the semiconductors industry, Fouad Boueri's career has spanned several functions, including product management, sales and marketing, channel management, and engineering management. Since 2020, Fouad has been a senior product line manager within the Defense and Aerospace business unit at Qorvo in the high power analog group. The product lines include discrete transistors, SSPA modules, and filters. Fouad holds an MSEE from the University of Michigan at Ann Arbor and an MBA from UCLA's Anderson School of Management. As senior product line manager, Paul Prudhomme is responsible for Qorvo's GaN MMIC power amplifiers. With 30 years of industry experience in customer-facing marketing and product development, Paul's primary focus is wireless systems from circuit-level design to full system architecture. Paul earned a BSEE in Communication Systems and EE from Northeastern University and an MBA from Southern Methodist University Cox School of Business. So with that, let me turn things over to the Qorvo team.
The agenda includes MMIC power amplifiers, transmit receive modules, and Spatium solid-state PAs. In the first section, we will review SWaP-C by mapping size, weight, power, and cost to system attributes in order to show areas where improvements are realized. We will highlight the semiconductor devices on the transmitter side that are available for amplification to achieve the system RF power requirements. For radar systems in particular, the attributes providing improvements to SWaP-C vary with frequency. This point will be illustrated with a comparison at S-band and X-band. Following this, we have notable examples of the value provided with new products that have recently launched to market. And the first section will finish with some hints about roadmap and the future we are working towards. In the second section, Fouad will present examples of interesting applications using Spatium. He'll provide an overview of the technology and then cover benefits and advantages of using Spatium compared to alternatives. and then we'll finish up with a portfolio overview. We participate in a competitive environment where there is an ongoing motive to continuously improve. In the context of phased array radar systems, there is a significant multiplier effect to any single improvement based on the number of transceivers that can range from hundreds to thousands. This graphic illustrates how size, weight, power, and cost translate to system improvements. As semiconductor technology advances, the benefits realized tend to be multifaceted. For example, from one generation of a power amplifier to the next, the improvements tend to be more than one attribute, such as higher efficiency, smaller package size, and less weight. Any one improvement to a multi-transceiver system accrues to the entire system. And anytime we can improve 2, 3, or 4 attributes, the accrued benefit is far larger for the overall system. Transmitter and receiver requirements vary greatly from system to system. Differences in frequency, transmitter power, transmitter gain, receiver noise figure, and receiver gain drive the requirements for individual components. The block diagram and images illustrate this point. Some systems are single transceiver, such as airport traffic control, while others can be thousands of transceivers. Qorvo offers commercial products for amplification as well as control functions from DC to over 40 gigahertz. The text on the left highlights transmit side capabilities in terms of RF power, semiconductor technology, MMICs, power FETs, and Spatium SSPAs. This graphic illustrates radar applications across frequency bands. An interesting comparison is S-band versus X-band. S-band's wavelength results in antenna spacing that is relatively large in comparison to the size of the electronics. In SWaP-C terms, the reduction in package size, as an example, from 10 by 10 millimeter SMT to a 7 by 7 millimeter SMT likely has less benefit, whereas a change from a hand-assembled flange package to SMT provides savings in manufacturing cost. Also, at S-band, a relatively small improvement in efficiency in the 2 to 4% range produces a large benefit in heat management and power consumption for a large array. At X-band, the wavelength results in an antenna spacing of about 1 inch. Packing electronics into an X-band system is a significant challenge, making size and integration important attributes towards SWaP-C improvements. In a sense, X-band applications lead to many opportunities to add value by offering improvements in package size, RF performance, and integration. This slide provides a very nice example of the benefits provided when comparing the previous generation MMIC-PA to a new generation MMIC-PA. These are both 3-stage amplifiers for X-band radar. The previous generation is a 50-watt device in a bolt-down flange package. The new device provides 60 to 80 watts in a surface mount QFN package. The QFN is 1/4 the size of the flange package and a fraction of the overall weight. Notice the difference in efficiency from 35% with the older device to 45 to 50% with the newer device. Overall, there are improvements across about 9 attributes in this example, providing a significant SWaP-C advantage. The X-band TR modules provide another concrete example of the SWaP-C benefits in moving from a discrete implementation for a 10-watt radar application to an integrated solution. Qorvo offers each of the functions in discrete SMT form with power amplifier, low noise amplifier, limiter, and antenna switch. Note the package size for each of these and then compare to the QPF5010, where the die from each of these on the left is integrated into the 7x5mm laminate overmold package. The value of the integrated TR module is evident in terms of reducing size, component count, the layout and routing complexity, and maximizing RF performance. The QPF0219 enables new possibilities for wideband applications. This product is a 10-watt transmit-receive module covering the 2 to 18 gigahertz frequency range. QPF0219 integrates 4 wideband die, the power amplifier, antenna switch, low noise amplifier, and limiter in an 8x8mm SMT package. The performance attributes are listed in the feature section with 20% efficiency on the transmit side and 4 dB noise figure on the receive side. QPF0219 enables next generation multifunction wideband systems with an SMT package in place of alternatives packaged in metal housings with wiring harnesses and coaxial interconnects. There is a clear benefit in size, weight, volume, and cost with this new product. Our product roadmap is multifaceted as we continue to invest such that higher value can be offered. It's a continuous process of improving and optimizing. We are working to improve our performance, increase integration, reduce size, and simplify overall customer implementation. For the TR modules, we first need to improve each of the RF building blocks, such as power amplifier, low noise amplifier, limiter, and TR switch, as well as invest in non-RF improvements that deliver SWaP-C benefits. Presently, we offer TR modules in S-band, X, and Y-band. And at X-band, there are 7 TR modules in production at this time, with others in development. While today's packages are die, wire bonded to 2D surface mount packages, there is investment toward 3D packaging solutions that are illustrated here. And for further details about product roadmap, please contact us, and thank you.
Thank you, Paul. And now it's time to go over Spatium SSPAs and see how they can achieve SWaP-C goals. We will start by giving an overview of the end applications, defining what a Spatium SSPA is, then expanding on the benefits of higher level integration. After that, we will describe the advantages over traditional solutions before finally presenting the Qorvo portfolio. One of the applications of Spatium SSPAs is a scientific one. It consists of mapping the moon's surface in a high-resolution fashion using a planetary radar. More details to come on the next few slides. Here is an example outcome from the high-resolution mapping using this planetary radar. What we're looking at is a 1.4 billion pixel image representing a 200 by 175 kilometer area on the moon called the Tycho crater and its surroundings. This planetary radar was able to achieve 5 by 5 meter resolution, which is the highest ever taken from the ground. Let's take a look at how this was made possible. The National Science Foundation's Green Bank telescope in West Virginia, with its 100-meter diameter, was used in a next-generation radar project, a cooperation between the National Radio Astronomy Observatory and Raytheon Intelligence and Space. It used a Qorvo Spatium SSPA QPB1316 at 13.9 GHz with an output power of 650 watt. The transmitted signal would bounce off objects in space and reflect to be received by the very long baseline array of 10 telescopes as receivers scattered around a large area of planet Earth. Its mission is to characterize near-Earth objects by measuring their shape, rotation, position, and composition. It allows for earlier, more precise analysis of smaller NEOs and reduces the need to launch space probes or satellites. All in all, it improves planetary defense by mapping large asteroid trajectories before they become dangerous to our planet. In addition to scientific applications, Spatium SSPAs can be used in SATCOM, electronic warfare, radar, and instrumentation. The Spatium technology is at TRL9, which is the highest technology readiness level at the DoD. It's field proven with over 1,200 units already shipped in the DNA airborne market. After having familiarized ourselves with applications of Spatium SSPAs, it's time to define what a Spatium SSPA is. It involves power combining of 16 MMIC PAs in a low-loss, compact, broadband fashion. It's built on a patented technology coupled with outstanding GaN performance in order to reach power levels, bandwidth, and efficiencies never achieved before. It is a reliable alternative to traveling wave tube amplifiers because it has a graceful degradation as opposed to the failure-prone, hard-to-get TWTs. Taking a look at the various components that go inside a Spatium SSPA and module can help us visualize the improvement in performance made possible by integration, in addition to other benefits and features. Starting with a wideband MMIC PA, spatially combining 16 of those, resulting in a cylinder that can be surrounded by a bias control card, capacitor bank, and heatsink, we end up with the Spatium SSPA product. In this example, the QPB0220N operates from 2 to 18 GHz at 18 volt with a CW signal at a saturated power of 220 watts. Going one level higher, we can add an integrated driver and then connectorize the enclosure, resulting in a multi-stage Spatium SSPA module QPR0220. Because of the multi-stage function, the gain is now at 38 dB. After that overview that helped us visualize how higher power, higher gain are made possible by the various building blocks that constitute a Spatium SSPA, let's take a look at the benefits and features. A Spatium SSPA provides higher efficiency over wide bands and over temperature at CW conditions than any other competing product. It also provides high power with reduced size and weight as compared to a total solution using legacy TWTs. In addition to that, the reduced total cost of ownership is made possible by the high reliability of solid-state technology as compared to the failure-prone TWTs. Finally, a yield improvement from the customer's point of view is made possible because it's a fully tested module as opposed to the customer having to purchase individual components and integrate them together by themselves. Looking at the integrated features, these include drain and gate control, low loss bias networks, drain pulsing, which means low power consumption and improved noise performance, fault detection, status monitoring capability, and internal temperature change indicators. The value proposition made it clear that Spatium SSPAs are superior to competing products. These competing products include TWTs as the legacy incumbent products and planar combining SSPAs as products using solid-state technology. However, the combining is done in a planar fashion rather than a spatial fashion. Let's start with Spatium SSPAs as compared to TWTs. In terms of bandwidth, Spatium can cover decade plus, whereas TWT is 1 or 2 octaves. For example, QPV0220N can cover 2 to 18 GHz as a Spatium SSPA. As for efficiency and CW power performance, they may be comparable, but when we look at the full solution level, including the power supply and other peripherals, Spatium SSPA-based solutions are smaller in size and lower in weight, making them suitable for the complex needs of customers. Indeed, for DC supply voltage, SSPAs operate below 50 volts, whereas TWTs need thousands or even tens of thousands of volts, which means lower platform power supply costs and safer operation when using Spatium SSPAs. The warm-up time for Spatium SSPAs is 0 compared to around 3 minutes for TWTs. This means lower energy costs for the customer as no backup is needed when using Spatium SSPAs. The harmonics are improved, meaning improved signal integrity. The power and gain response is flatter, and the failure characteristic is graceful, as opposed to the single point of failure with TWT. That is a major advantage, as when the equipment is in the field and experiences some harsh conditions, perhaps outside the recommended operating conditions, making it fail, then it's easy for the Spatium-based solution to continue operating with a slightly lower performance, while a TWT completely fails and needs to be replaced right away. This translates into a lower total cost of ownership when using Spatium SSPAs. The design reuse is high with Spatium SSPAs, meaning lower overall solution price. The saturation is flat, whereas with TWTs, P out gets reduced if you go closer to saturation. In terms of reliability, solid state means more than 1 million hours of mean time between failures, whereas for TWTs is around 30,000 hours. Finally, in terms of availability, there's a low risk for Spatium SSPAs, whereas TWTs are getting harder and harder to get. So we consider this as a high risk for TWTs. As we saw in the previous slides table, Spatium SSPAs are preferred over TWTs, mainly because of reliability, total SWaP-C parameters, and wider bandwidth. We can say that Spatium SSPAs provide a more reliable, easier to use solution with reduced size, weight, and total cost of ownership as compared to solutions based on their closest TWTA counterparts. Compared to TWT amplifiers, the QPV0220N covers a wider frequency band, 2 to 18 GHz, than any available competitor product. category of competing products is planar SSPAs. How do Spatium SSPAs differentiate as opposed to planar SSPAs? Well, over wide frequency bands and over temperature at CW conditions, Spatium SSPAs provide higher output power and efficiency than any other known solid-state product in the industry. The customer could benefit from using a Spatium SSPAs as opposed to designing with planar combining PAs in terms of saving on energy consumption, higher efficiency at wider frequency bands and tougher conditions like CW over temperature, saving on design costs because the integrated product includes the combining peripherals and can be multi-stage in an enclosure, and with superior quality and support due to the vertical integration at Qorvo, meaning the die, the assembly, and the test are all Qorvo. After the overview that showed how Spatium SSPAs are superior to competing products, let's take a look at the various nodes offered by the Qorvo product line. The microwave node covers 2 to 20 GHz, the millimeter wave node covers 18 to 40 GHz, while the high power microwave node covers 8 to 16 GHz. Naturally, size and weight go down as we go up in frequency. Starting with the microwave node, the cylinder that houses the combined MMICs is at a size of 11 by 2.3 inches, while for millimeter wave, it's a 3.8 by 2.5 inches, and high power microwave node is somewhere in between here at 8.3 by 3 inches. The weight also depends on the metal used. So with aluminum, it would be lighter, 2.6 pounds versus 0.8 pounds for microwave versus millimeter. And with copper, it would be 6.3 pounds versus 2.1 pounds for microwave versus millimeter. Finally, for the product size as a whole, 11 by 4 by 3 inches for microwave node, 4 by 4 by 3 inches for millimeter wave node, and 9 by 6 by 5 inches for the high power microwave node. Now that we're familiar with the 3 nodes that the Qorvo product line offers, let's take a look at how this translates in terms of platforms of products. Looking at this slide with the x-axis representing frequency, the 2 to 18 GHz portion on the left side of the slide shows the microwave and the high power microwave products. Starting at the bottom with 20 watt power level drivers, we can reach above that 100 to 200 watt for Spatium and module products in the 0218 category. For the 0220 category, you can reach up to 315 watt. And if you cover a narrower bandwidth like 2 to 6 GHz or 6 to 18 GHz, then power level can go up to 350 watt. As for the high power microwave products, they are shown on the top left. These are QPB 1024 up to 740 watts and QPB 1316 up to 650 watt. Note that these 2 products in the high power microwave node include a liquid cooling jacket. As for the millimeter wave node, that covers K and Ka band, 18 to 40 GHz. We do have a QPB 2040N that goes up to 125 watt, and narrower bandwidth products like the 27 to 31 GHz product up to 220 watt, and the 32 to 38 GHz product up to 150 watt. Finally, the QPB 1111 covers a narrower band 34 to 36 GHz with up to 350 watt. For support and design resources, there are many ways you can reach Qorvo. For technical support, appsupport@qorvo.com. For general customer support, customer.support@qorvo.com. As for access to design tools, white papers, technical articles, and block diagrams, please visit our design hub available on our website. Finally, for inside sales, you can reach inside.sales.global@qorvo.com. Thank you for attending this webinar. The key points that we covered are Qorvo's advances in MMIC and TR modules, driving all SWaP-C improvements, Spatium SSPAs enhancing reliability and reducing costs in radar, EW, and SATCOM applications. And finally, how Qorvo supports the design community's innovations by providing access to various tools and support personnel. Qorvo SWaP-C exceeds design goals. Thank you.
Well, great. Thanks, Paul and Fouad, for that presentation. That was interesting and certainly lots of good information. Now let's take a look at the audience questions. And please remember, it's not too late. You can still submit a question in the Q&A window, and let's get started. Now, based on when this question came in, Paul, I think it was during your portion of the presentation, but you probably both will have a comment on this. And the question is the increase in efficiency due to the implementation of GaN?
Relative to gas, yes. And for GaN Qorvo runs maybe 4 nodes of GaN right now. There's plenty of activity to improve efficiency with changes in modeling, changes in process. So there's efficiency is multifaceted. But you take a 4-watt GaN device compared to maybe a 4-watt gas device, the difference in efficiency is pretty significant for GaN versus GaN.
Great, thank you. Fouad, any thoughts from the Spatium side?
No, I would agree with that assessment. Spatiums are basically a combination of 16 MMICs, so that would translate on the higher level assembly. We also have a 93% efficiency in terms of combining at the Spatium level due to the patented spatial combining technique.
Good, thank you. Next question. What limiter power handling are you, lost my question here, bear with me. What limiter power handling are you considering for 1 to 18 gigahertz CW and pulse duty cycle?
Paul, any input on that? So limiters would be under a product line whose product line manager is not with us today. We can definitely relay this question and get back to you.
Okay. Next question. How did you improve PAE 10 to 15% from former packaging to the QFN versus flange?
Yeah, that would be a question for Paul.
Yeah, sorry, Eric. My audio is breaking up on this side. Could you repeat that, please?
Sure. How did you improve PAE 10 to 15% from former packaging to the QFN versus flange?
Yeah, it's just a newer generation of GaN die for the most part. It's, I would say it's somewhat independent of package. It's back when we built that flange package at 50 watts at X-band. That's the performance we're getting at the time. I mean, there is some coating that does help with the loss of mole compound. So there's some benefit to some coating over the die that helps with the QFN over mold material.
Great, thank you, Paul. Is it possible for Spatium SSPAs to operate below 2 gigahertz and or above 40 gigahertz?
So the two factors that play into this consideration would be the MMIC capability and the combining technology. In terms of MMIC capability, if there is a MMIC, and I think we do have a MMIC that can go below 2 gigahertz, then a Spatium would be possible. It's currently not in our standard product line, but if there's a business case, we can definitely consider developing such a product. Same thing applies for above 40 gigahertz. MMIC development is on the roadmap for these high frequencies, and that would be possible once we have a MMIC for it.
Alrighty, good, thank you. What would it take for Qorvo to design a custom or semi-custom Spatium product?
So in order to validate a business case, we would need a certain credible revenue forecast, sufficiently large quantities for a healthy ROI. Semi-custom or custom developments usually require some form of NRE funding. Could be upfront or distributed over an initial advanced PO. It usually covers a major portion, if not all, of the development budget. And we usually like to see a forecast in time frame of 5 to 7 years or more. So definitely possible. Like any other product, a Spatium can be developed based on custom requirements. It just has to meet all these prerequisites for us.
Yeah, that makes sense. It has to make business sense.
Yeah, and in addition to being technically feasible, right? So the engineering team would have to plan and give us an assessment whether it's feasible technically.
Good, thank you. Are there more QPR modules that are expected to be released in the future?
Yes, definitely. At the moment, we're launching next month QPR 0220, which covers 2 to 18 gigahertz. To follow would be other QPR modules that cover 6 to 18 gigahertz, 32 to 38 gigahertz, and 18 to 40 gigahertz.
All right, great, thank you. What are the products on the TR module roadmap?
Yeah, we've at X-band we now have 6 products that are production status, with another 2 in development, and a pretty healthy roadmap at X-band. Just incorporating customer feedback and then looking at making improvements. And then one of the variables is how much power does array want to operate at, so that can drive development in different ways. We've got first wideband 2 to 18 10-watt TR module was introduced recently. We've got a 2-watt in development, and then we're always looking at where we can apply this multi-die TR module capability to other parts of the frequency range. So if there's something in particular that's of interest, please contact us. And also you can contact us to see our roadmap. Thank you.
Great, thanks, Paul. What thermal improvements were implemented on the QFN package?
On the package itself, there were, I can't say that there's thermal improvements with the package itself. It's just that the efficiency of the amplifier increased quite a lot. So that's a 10 to 15% improvement in efficiency. That's just process capability, design, modeling.
All right, good. Just checking to see if we get any last minute questions, and I don't see one. So with that, I'd like to close the webinar here. And I'd like to thank Fouad and Paul again for the presentation and for answering questions. And I'd also like to thank our sponsors, RFMW and Qorvo. And I'm sure it's been a very useful presentation for the audience. As I mentioned, the webinar has been recorded and it'll be available to watch later today. You'll find it in the events section of the Microwave Journal website under the archived webinars and events tab. So please feel free to watch it again or share it with any of your colleagues who may be interested And remember, if you aren't already a subscriber to Microwave Journal, you can sign up on our website. The subscription is free to members of the industry. And let me close by saying thanks to everyone for joining us today. Keep an eye out for upcoming webinars and panel sessions, and I hope you all enjoy the rest of the day.